Let me know about the audio. Okay.
Hello, everyone. My name is Ines Chami. I'm a Ph.D. student at Stanford University, and my research is focused on learning representations for graph structured data, and I'm more specifically focusing on hyperbolic embeddings and learning representations in non-Euclidean spaces. And so in this talk, I will give some introduction to hyperbolic embeddings and also go over some applications that I've been working on in the past few years. All right, so to put some context, graph structured data is relational data that comes in the form of nodes and edges. This data is ubiquitous in the world and appears in many real-world problems, such as biology, for instance. Phylogenetic trees can be represented as trees which are a specific form of graphs. Molecules in chemistries are also represented as graphs where the nodes or entities are atoms essentially, and the relationships between them are the chemical interactions. The internet can also be represented as a graph of web pages and click between them. Recommender systems are represented as graphs where the interactions are between users and products. Knowledge graphs and knowledge bases are very common relational data. Natural language processing can also play with graph such as parse trees. And so essentially this data is critical in many applications. And so it's important to know how to use graph structured data and the information that comes with it. And so this is the goal of this presentation. And so formally the way people do this, at least for machine learning tasks, is using network embedding or graph embeddings. And so given the input, which is a complex relational structure, usually discrete, sparse, and high dimensional, we want to map the discrete objects to embeddings, which are low dimensional, continuous, and usually dense representations. And so this compressed graph representation should preserve the information that was available in the original discrete graph structure. So for instance, if I have two embeddings for nodes in the graph, and I know that the nodes are similar in the input graph, then one would hope that the embedding preserve that information, such as by making the points close in the embedding space. And so once we have such embeddings, it's very common to use them in downstream machine learning tasks, such as predicting new edges that weren't observed in the original graph. So that's common in recommendation system, but also predicting labels about the nodes for like classification tasks and etc. So network embedding is a major part of machine learning when one's deal with structured data, graph structured data. All right, so in today's talk, I'll first start by reviewing some basics of Euclidean embeddings and show how they're being trained to represent graph structured data. I'll then move to hyperbolic geometry and try to provide some intuition for why this geometry is a good candidate to represent some specific graph structure, and especially tree-like and hierarchical graph structures. I'll then describe how we can learn hyperbolic embeddings using hyperbolic distance and different optimization tricks. And I'll then describe a recent application that I've been working on, which is knowledge graph embedding, describe our approach to learn hyperbolic knowledge graph embeddings, and also show some results on the link prediction task. So let's first recall the problem of network embedding and how usually these methods are learned. So the input is a graph, which comes with vertices and edges between them. Usually edges have weights that indicate the similarity or dissimilarity between the edges. And so in this work, we consider edge weights to indicate similarity. And then the output is going to be embeddings for each node in the graph. And usually the way these methods are learned uses 4 components. So the first one is the choice of the embedding space, which is commonly taken to be the Euclidean space. And this presentation will be exploring how to move away from these Euclidean embeddings and use other non-Euclidean embedding spaces. The second component is an encoder, which essentially maps the input vertices to the embeddings, the continuous representation in the embedding space that was chosen in step 1. And so there are different ways to do this encoding, and the simplest way is just to do an embedding lookup, like a vocabulary which assigns the vertex ID to the embedding. The third component is the scoring function, which essentially is going to assign scores to pairs of edges, pairs of vertices, sorry, based on their embeddings. So one could, for instance, take the negative distance or inverse distance or inner products. There are different ways to measure this similarity, but the intuition is that it should assign a similarity score to pairs of vertices. And finally, the fourth component is the choice of a loss function, which will be used to train the embeddings. And so we usually minimize this loss function using the observed data, the observed edges that are present in the graph to get the final output embeddings. And note that there are different ways to do this, and one may also consider having input node features, and this is usually the case of graph neural networks. For the purpose of this presentation, we'll not go into details of graph neural networks, but note that this is also another possible way to learn graph embeddings. So here are two examples of Euclidean embedding methods for graph structured data. So the first being inner product methods. So in these methods, the encoder can be just a simple embedding lookup, mapping vertex IDs to embeddings in d-dimensional Euclidean space. And then the scoring function is a simple inner product between the embeddings in the Euclidean space. And then these embeddings can be learned by minimizing a loss function, which essentially measures the distance from the predicted score to the ground truth score, which are given by the edge weights between vertices. And another type of methods is distance-based methods. So in these methods, similarly, the embedding encoder can be a simple lookup. But here the score is proportional to the Euclidean distance in the embedding space. So given that score means more similar, it's common to take either negative distance or inverse distance to measure similarity between nodes. And then again, loss function is going to be such that pairs with high input similarities are going to have small distances, and pairs with small input similarities should be further away in the embedding space. And so we know that in both these methods, the training part and the inference part really rely on the Euclidean geometry and like Euclidean operations such as inner product, L2 distances, etc. And so in this talk, we're interested in exploring non-Euclidean embeddings and how can we make the embeddings lie in non-Euclidean spaces. And so as we saw previously, Euclidean embedding methods really rely on Euclidean geometric operations and properties. So for instance, the length or the distance between 2 points is going to be measured by the length of the straight line connecting them, which is the Euclidean geodesic. But then if points lie on a curved manifold, we know that this line is actually curved, and so we have to use a different formula to measure the arc length between 2 points. And so we'll see how technically we can make embeddings lie into non-Euclidean spaces and use those embeddings in practice. And we'll also see that for some type of data and structure in the input graph, non-Euclidean embeddings can be a very good candidate to match the geometry of the input graph. And so first I'd like to provide some historical context about the development of non-Euclidean geometry, which is a quite interesting story. So we're all familiar with Euclidean geometry, which is probably one of the oldest mathematical systems developed by Euclid, and which relies on 5 postulates. The first 4 postulates have a very simple form, and the 5th postulate, which is also known as the parallel postulate, is stated as follows. Given a line and a point not on the line, there exists exactly one line parallel to the given line that can be drawn through the point. And so this fifth postulate has a much more complicated form than the other four, and this gave rise to many controversies among mathematicians for many centuries. And essentially, they were trying to prove that the fifth postulate was a consequence of the other four with no success. And it's not until the 19th century, with the work of Gauss and other mathematicians, that non-Euclidean geometry was discovered by essentially using alternative forms of the fifth postulate. And so, for instance, spherical geometry says that there is no parallel lines that can be drawn through a point, and essentially the lines curve toward each other until they meet at some point. So they're not parallel. And hyperbolic geometry, it's a different scenario where there are infinitely many lines that can be drawn through a point, and so the lines curve away from each other. And this finding of the discovery of non-Euclidean geometry led to major scientific advances in physics, for instance, where the development of the theory of general relativity by Einstein was enabled by tools of non-Euclidean geometry. And so in the context of hyperbolic geometry, the fact that it has a constant negative curvature and that lines curve away from each other makes it behave really close to trimetrics. In some sense, hyperbolic geometry is like some sort of continuous version of trimetrics. And there are several properties to illustrate this statement, the first being the exponential volume growth. So given some radius and a hyperbolic space, as we increase the radius, the volume of a ball is going to grow exponentially, whereas this growth is only polynomial in Euclidean space. And this is similar to trees, where if we increase the depth of a tree, let's say a full binary tree, then the number of nodes is just going to grow exponentially every time we increase the depth. And so this type of behavior makes a hyperbolic space a really nice candidate to represent tree data, because in some sense it has more room to fit the data. And for instance, in this circle illustration, all the objects which are bats have the exact same size in hyperbolic space, but we see that as we get closer to the boundary, these things get infinitely smaller, and this illustrates the exponential volume growth property. And another property is the fact that triangles are thin in hyperbolic space, in the sense that the length of the largest side of the triangle is going to approach the sum of the lengths of the other two sides. And this is also a property that is close to trimetrics, in the sense that we can decompose distances into sum of distances. And so these connections between trees and hyperbolic space lead to very nice properties to embed trees or hierarchical data in hyperbolic space. And so, for instance, Sarkar in 2012 introduced a combinatorial construction to embed trees in hyperbolic space using only 2 dimensions with arbitrarily low distortion. So this is a pretty strong property for hyperbolic space. And more generally, we can embed graphs with hierarchical structure with low distortion compared to Euclidean space. And so in practice, we can use many tricks to make the embeddings hyperbolic-like. So this is the example of Poincaré embeddings, which was introduced by Maximilien Nickel in a NRIPS paper, 2017. So going back in our previous slides, we had an encoder and a scoring function, and we still have those elements in hyperbolic embeddings, but we'll have to modify them slightly. So the encoder is still going to be an embedding lookup, but if we work with the Poincaré model, which is the unit ball, then we want to make sure that points remain in the ball. And so we have to use projections to ensure that the norm is less than 1. Note that there exist other models of hyperbolic space. And here I'm describing the Poincaré, which has been widely used in machine learning. And then we had a scoring function, which is now going to be depending on the hyperbolic distance function between points rather than the Euclidean distance. And the embeddings can be learned using similar loss functions as we've seen before, except that we have to use Riemannian optimization rather than standard Euclidean optimization techniques. And the reason for this is that we want to make sure that points remain on the manifold after we apply the gradient step. And so Riemannian gradient descent is a technique to do so. And essentially it uses a technique called retraction to move around points that are on the manifold. All right, so let's now look at some applications of hyperbolic embeddings, and more specifically, we can look at hyperbolic knowledge graph embeddings. So to recall the setup of knowledge graph embedding, which is slightly different from network embedding that we've seen before, we're given a knowledge graph. So we still have vertices, but now the edges have types. We can have different relations essentially between vertices. And so these knowledge graphs usually come in the form of triplets, head, relation, tail, representing relations between entities. And so the way we learn embeddings for this graph is still by picking an embedding space. And then we also have a mapping from entities to the space. But we also now have to consider a mapping from relations to embeddings, which are essentially going to be transformations modeling the relationship between entity. And then we still have scoring functions, but now the scores are being assigned to triplets rather than pairs. So we want to score a head, relation, tail triplet. And the optimization step is similar as before. We minimize a loss function using the observed data and try to maximize or minimize some objective to make sure that the embeddings preserve the relationships that we had in the input knowledge graph. One important challenge about these knowledge graphs is that the relationships found in knowledge graph are usually very complex and diverse. And so they may have very different patterns. So for instance, here we see that Barack Obama is married with Michelle Obama and the relationship is symmetric. Michelle is also married with Barack Obama. But then we have other relations like father of, which are hierarchical and unidirectional. So if Barack Obama is the father of Malia Obama, the reverse is not true. And so when we represent these entities using embeddings and the relationships using geometric transformation in the space, we want to make sure that these transformations capture all the logical and hierarchical patterns found in the original data. And this is really hard to do in general in Euclidean space. And so previous work have been using very high dimensional embeddings to capture all these patterns, but this is obviously expensive to store and leads to memory issues. So we're interested in overcoming this limitation by using low dimensional embeddings. And so in our work, we've been exploring how to use hyperbolic embeddings for knowledge graph representations. And the main motivation is that hyperbolic embeddings can represent hierarchical data in low dimensions with high fidelity. But we still need to capture all the logical patterns such as symmetry, antisymmetry, inversion, etc., that we find in knowledge graphs. And so the way we do this is by representing relationships using rotational operators. And the reason why this is interesting is that rotations have many properties that make them a good candidate to represent logical patterns. So for instance, if I take a rotation of angle pi, I know that if I apply the rotation twice, I end up in the original position. So it's just the identity. And this is similar to symmetric relationships. For instance, Barack Obama married with Michelle Obama is married with Barack Obama. And so the nice thing about hyperbolic space is that rotations in the Poincare model that are centered at the origin are isometries of the space. So applying them on the embeddings is not gonna affect the geometry of the data, and these are valid operations essentially, and so we can use them safely in the hyperbolic space. And so the way our approach works is still using mappings from entities and relations to embeddings. So we map head and tail entities to points in the Poincare ball and use projections to make sure that they remain on the manifold. And we also map relations to rotation matrices, which we can parameterize efficiently using Given's transformation, which are just 2x2 matrices. So the output rotation matrix is very sparse and can be applied in linear time. So this is computationally efficient. And then we have a scoring function to score the triplet head relation tail, which is going to be measuring the hyperbolic distance between the transformation of the head entity and the tail entity. So we hope that after applying the rotation matrix to the head entity, we end up somewhere close to the tail entity. And so in summary, this approach captures both the hierarchical structure found in knowledge graph, but also the logical patterns that we find in these graphs. And one trick that I would like to point here is that we're using a trainable curvature. So I didn't talk in detail about curvature before, but essentially it measures how hyperbolic and tree-like the space is going to be. And so zero curvature is just recovering the Euclidean geometry. And we'll show in our experiments that using these trainable curvatures gives more flexibility to the model, so that relationships that are hierarchical are going to get low negative curvatures, and relationships that are not so hierarchical, like symmetric relations, are going to get curvatures that are closer to zero, essentially. And so here I'm showing some results using our proposed approach for knowledge graph embeddings. So we're comparing two Euclidean embeddings that have been proposed in the past, and one important model is Rotate, which essentially uses this idea of modeling logical patterns with rotations, but this is done in Euclidean space. And we're also comparing to an existing hyperbolic model that doesn't use rotations to represent the transformation and only uses translations in hyperbolic space, which might not be very expressive to capture different patterns. And so on these two data sets in low dimensions, we see significant improvements over previous approaches using both the hyperbolic embeddings and the rotations. So this suggests that modeling both logical patterns and hierarchical structure in graphs is important for knowledge graph embeddings. And the next experiment is analyzing the role of curvature. So as I've mentioned before, we use trainable curvatures per relation so that the model can adapt the curvature of the space based on how tree-like the relationship is. And so in low dimension, we see that hyperbolic embeddings lead to significant improvements over the Euclidean embeddings. So these are the red and blue curves. And in high dimension, we see that the hyperbolic and Euclidean, with trainable curvature and the Euclidean have better performance than a hyperbolic with a fixed curvature. And so the reason for this is that when we have enough dimension, then the Euclidean embeddings are just expressive enough to capture different patterns in the knowledge graph, whereas fixing the hyperbolic curvature is going to lead to precision issues. And so this actually degrades performance in high dimension. So the takeaway here is that using trainable curvature gives more flexibility for the model to adapt to the given dimension. So to summarize this talk, we've seen how to use hyperbolic embeddings in practice. So it starts by picking a hyperbolic embedding space, for instance, the Poincaré ball, and using projections to make sure that the embeddings remain in the desired space. We also need to use a distance function, which is going to depend on the choice of the geometry. So for instance, the Poincaré distance function, and this can be computed exactly and implemented in Python or other frameworks. We have to use Riemannian optimization to make sure that the points remain on the manifolds. And the bonus that we proposed is using trainable curvatures to represent, for instance, relationships in knowledge graphs, or even the curvature of the embedding space, just to give more flexibility to the models to adapt to the curvature of a relation, and also avoid the numerical issues that may arise in higher dimensions. So these embeddings are useful for graphs that have a tree-like structure or hierarchical graphs, such as taxonomies. And we see benefits from using hyperbolic embeddings in low-dimensional regimes, especially. So in higher dimensions, both Euclidean and hyperbolic embeddings achieve similar performance, and this is because we just have enough capacity to represent complex relationships between input vertices in higher dimensions in both Euclidean and hyperbolic spaces. And in terms of applications, we've looked at how to do knowledge graph embedding in hyperbolic space, but note that there are many other applications that I didn't mention in this talk, such as word embeddings, hierarchical clustering, question answering, etc. Thank you very much for listening to my talk. I'd like to thank my collaborators with whom this work wouldn't have been possible. If you have more questions or want to learn more, we have papers, blog posts, and you can find them on my website. And you can ask me any question in the Q&A session or contact me by email. I'd be happy to answer any questions that you might have. Thank you.
Thanks, Ines, for the wonderful talk. So we have time for one or two quick questions. So there is one question from Arijit. So do you want to ask the question?
Sure. So I was just curious, did you look at the hyperboloid model for the hyperbolic geometry or just the Poincaré one?
Yeah, so just for the audience that doesn't know about the hyperboloid, there are 5 models of hyperbolic geometry. The Poincaré ball is one of them, and the hyperboloid is also one of them. In these specific experiments of knowledge graph embeddings, we use the Poincaré ball model for the reason that rotations that are centered at the origin coincide with Euclidean rotations. So it's very easy to compute them, whereas in other models, that's not necessarily true. We have other works where, for instance, we wanted to compute inner products between points, and in those works, we use the hyperboloid model because there's a correspondence with the Minkowski inner products. So it really depends on the task we want to do, but all models are geometrically equivalent. So in terms of performance, it shouldn't matter. It's more practical choices.
All right, thank you.
Thanks.
So I have one question. So I was just curious. So if there were already any ideas to exploit entity type hierarchies through hyperbolic geometry?
Entity type, you mean trying to get embeddings of the types themselves rather than the entities?
Right. So for example, Barack Obama is a president. President is a type of politician, and politician is a type of person, this hierarchy.
Yeah, definitely. I think so. I haven't worked on that, but there's a project in our group where they wanted to do named entity disambiguation. And so they tried to inject signals from many sources, and types was one of them. So you may have different types, like 2 entities that share the same string, but they have different types. And so types can be used to disambiguate between entities. And as you said, there are latent hierarchies in those types. So they were considering using hyperbolic embeddings for the types just to like have better quality in the embeddings, and use that in a natural language processing model that will be used to disambiguate. So definitely that's something that can be done.
Cool. So thanks a lot for the